Welcome back to another video. It's your favorite math professor here, Dr. Tarcia Hubert. In this video, we are going to talk about the mean and standard deviation of a binomial random variable, okay? It sounds complicated, but it is not. Just follow with me, okay? So in the last video, we talked about how to construct a binomial random probability distribution. And so we had N, which represented a number of trials, and we had P, which was the probability of success, and then we had 1 minus P, which was the probability of failure. And you're going to use those same variables in calculating the mean and the standard deviation. So the mean of a binomial random variable is found by taking N, the number of trials, times P, the probability of success. And the standard deviation of X, a binomial random variable, is found by taking the square root of N times the probability of success times the probability of failure, okay? So two pretty simple formulas. Those will get you the mean and the standard deviation of a binomial probability. So here's an example. According to flightstats.com, American Airlines flights from Dallas to Chicago are on time 80% of the time. So suppose 100 flights are randomly selected. All right, 100 flights are randomly selected. What we want to do is we want to compute the mean and standard deviation of the random variable X, which is the number of on-time flights. So our two outcomes here is whether the flight is on time or not, okay? So that's what makes it a binomial. Well, one of the criteria that makes it a binomial experiment. We want to calculate the mean and the standard deviation. So first we need to identify what is N. Our N in this case is 100 because there are 100 flights that are randomly selected. So here, this gives us our N. Our P is going to be the probability of success, which is this 80%. That's that they're on time. Our success is the flight is on time. So the probability would be 0.80. And then the probability of failure, which is 1 minus P, is going to be 0.20 because that's 1 minus 0.8. So the mean of X, that's mu of X, is going to be equal to 100 times 0.80, which is equal to 80. So the mean is 80, and basically what that mean is, I think that's the next part we're going to interpret the mean. So I'm going to hold off on that, and now I'm going to calculate the standard deviation. So sigma of X is going to be equal to the square root of N, which is 100, times P, which is 0.80, times the probability of failure, which is 0.20, or 1 minus P. So if you multiply all that out, you end up getting 16 underneath the square root, and the square root of 16 is 4. So your standard deviation ends up being 4 flights, okay? So remember that's a measure of spread, so it tells you how far spread out. Well, not completely how far spread out, but it kind of gives you an idea of the spread of the data, all right? So that is how you would calculate the mean and standard deviation. You would just use those simple formulas. Mu of X is equal to N times P, and sigma X is equal to the square root of N times P times 1 minus P. So now we want to interpret the mean. So just exactly what does that mean? So what that means is that we can expect in a random sample of 100 flights from Dallas to Chicago, about 80 of them will be on time. Because remember, we're measuring whether the flight is on time or not. And since the mean is 80, that means if we sample 100, we can expect 80 of them to be on time. Okay? And then the next question is, would it be unusual to observe 75 on-time flights in a random sample of 100 flights from Dallas to Chicago, and why? All right. Now, in order to answer this question, we need to know like the distribution of the data. And one thing you could do is you can graph the data and kind of see, is it symmetric, or is it skewed left, or is it skewed right? Or you can use this rule here that says for a fixed P, as the number of trials in a binomial experiment increases, the probability distribution of the random variable X becomes bell-shaped. So bell-shaped means it's symmetric, but as a rule of thumb, if N times P times 1 minus P, and if you notice, that's the part that was underneath the square root. Sorry, I went the wrong way. That's the part that was underneath the square root in the standard deviation formula. It was the square root of n times p times 1 minus p. Well, the rule of thumb says that if the value that's underneath there, we call that the radicand, if that's greater than or equal to 10, then the probability distribution will be approximately bell-shaped. So in our case, our n times p times 1 minus p was 16, which is greater than or equal to 10. So that means our data that we're looking at is bell-shaped. And since it's bell-shaped, the empirical rule applies. All right, remember the empirical rule? We talked about this a while back. If you have a bell-shaped data, that looks like this, remember the empirical rule says, okay, here's your mean, and the majority of your data lies within 3 standard deviations. So remember that was mean minus 1 standard deviation. We called it S. That was mean minus 2 standard deviations. Mean minus 3 standard deviations. Plus, not minus. Mean plus 1 standard deviation, mean plus 2 standard deviations, and mean plus 3 standard deviations. And then when you go this way, it's mean minus. So this is mean minus 3 standard deviations. And we use X bar to represent sample. So either mu or X bar. But basically, the empirical rule tells us that the majority of our data lies within 3 standard deviations of the mean. Anything outside of those 3 standard deviations is unusual or unlikely. So in this case, our mean was 80 and our standard deviation was 4. So if we want to figure out what's within 3 standard deviations of the mean, then we would do 80 minus 3 times 4 and 80 plus 3 times 4. So this is the mean minus 3 times sigma, and this is the mean plus 3 times sigma. So 80 minus 12, that gives you 68, and 80 plus 12, that gives you 92. So that means the majority of our data lies between 68 and 92. Anything outside of those regions would be unusual. So I actually, so part C, which, I don't know, I'm on the wrong slide, but anyway, it asked if it would be unusual for 75 flights to be on time. Since 75 falls within this range, 75 will be in here somewhere, then that's not unusual. That's pretty usual. If it falls outside, meaning bigger than 92, if it was in this region here, or less than 68 in that region there, then it would be considered unusual. Hopefully that makes sense, okay? And that was the answer to this last part. Would it be unusual to observe 75? So no, it would not be unusual. And that's because it falls within 3 standard deviations of the mean. Another way you could do that is find the probability of 75 and see if it is close to 0, which we've done before in the past when determining if something is unusual. Remember, the closer it is to 0, the more unusual it is, the probability. So this is how you will calculate the mean and standard deviation of a binomial probability distribution. If you have any questions, don't hesitate to ask them. Thank you for watching, and I will see you in the next video. Thank you.